Shall we do it?
Okay, so I request Mohan to chair today's session. Yeah, so Mohan, please. Yeah.
I have great pleasure in introducing Ritvik Ramkumar for today's talk, an invitation to the fiberfull scheme. Ritvik, shall we start?
Yeah, we can start. Okay. Thanks for the introduction. I'd like to thank the organizers for inviting me to give this talk, and it's a pleasure to be here. So yeah, my talk today will be on the fiberfull scheme. This is a joint work with Yaron Sidris, who is in the audience. And I'll try to keep this relatively gentle, and I sort of want to convince you that this is an interesting scheme to study. And that'll be the goal of today's talk. Okay. So I'll fix some notation for the whole talk. Ideals are assumed to be homogeneous. All schemes in rings involved are locally in the theorem. If I don't say it, R will always denote a graded polynomial ring, and script M, if you see it, will be the maximal ideal. Any other notation I use, you'll see me define it as I go along. So I guess the motivating question is to study families of I'm going to stick to homogeneous ideals because I want to think of projective varieties. I want to study families of homogeneous ideals inside the polynomial ring. So subschemes of projective n space. And I want to fix some numerical data satisfying some numerical data. Right? So what I mean by that will be made precise as we go along, but that's the goal. So we want to study families of homogeneous ideals. We figure out what family means and what these numerical data is. Okay? So to study such a thing, what you want to do is construct some big moduli space. So some bigger scheme whose points are somehow in natural bijection with these homogeneous ideals. So if we fix the numerical data to be the Hilbert polynomial, growth and deconstructed such a moduli space. And now I'm going to define it. So I'll first sort of define it a little bit well, you'll see. Okay. So growth and dec are the following. So P be a numerical polynomial. So this just means it takes on integer values. There is a scheme Hilb P Pn. So this is the notation. So the Hilbert polynomial goes at the top as a superscript, and as a subscript, it's the ambient space called the Hilbert scheme. So and that parametrizes closed subschemes Z and Pn with the polynomial P. So that's what it's doing, but sort of very explicitly, what exactly is this as a set? That's the following. Okay. So I can write in terms of ideals. So I mean, the subvariety of Pn is just cut out by some ideal. So it's the ideals of the polynomial ring.
So what's a numerical polynomial?
So just think of a polynomial with rational coefficients such that all its when you validate any integer, it lies in the integers. So
Okay, thank you.
So this is just convenience, but you can just imagine P is the Hilbert polynomial. Okay, so in fact it is it does compute the dimensions of each graded piece of some ideal.
Mm-hmm.
So it's sort of all ideals I that are homogeneous, saturated with respect to the maximal ideal, And as we were just saying, the coordinate ring has dimension PV for all sufficiently large P. Okay, so at least at the level of sets, and so if I say this, I mean at the K points of the scheme, we have this identification. So this is what we mean by saying like there's a natural bijection between the points of the scheme to the set of all ideals. So before I get into the details of this, let's just see an example, a very simple example. And that's of a plane curve. Okay, so by a plane curve, I just mean this variety colored by one equation, f of degree d. F is degree d. Okay. So that's what a plane curve is. What is the Hilbert scheme of a degree d plane curve? So let's see. So the Hilbert polynomial of a plane curve is given like this. So it doesn't really matter what it is, but just know that this is the Hilbert polynomial. So once we have fixed this, we can talk about all, I guess, ideals with this Hilbert polynomial. So everything with this Hilbert polynomial, it turns out, is a plane curve of degree d. So this is the collection of ideals colored by one element of degree d. And usually you want to think of this as the projectivization of the space of monomials of degree d, right? Because defining f is just a linear combination of the monomials of degree d. So this is in fact nothing but the projectivization of the space. And so this is isomorphic to t plus 2 minus 2. Okay. So the collection of forms of degree d, aka plane curves of degree d, is actually itself a projective space. And this is kind of, the reason why you want to study the family of all these objects is because by doing so, you actually end up understanding more about the object itself.
Ritvik, a quick question. May I enter? Yeah. So this is just a set so far, Hilb.
Yeah, that's
ENK.
right.
It is just a set, or
no,
there's more structure involved?
It's a scheme, but as a set, it sort of at the level of K points, as a set, it's in natural bijection with the set of ideals. Let's put it that way. So it is a scheme. I will make this more precise, but this itself is a variety.
Okay.
But its points are in natural bijection with the set.
Okay. Okay. So the scheme structure is not clear to me.
Yeah, it's nice. I've not. So yeah, I'll make this a little bit more precise in a second. Yes, it's right. I've not told you what the scheme structure is.
Okay.
That's right. That's right. So what you're getting at is I'm being sloppy with equality, and that's true. So all I've said here is at least as sets, these two are the same. But it turns out that even this as a scheme, it's actually going to be isomorphic to this. So if you actually run through the construction, the Hilbert scheme of a plane curve is actually on spot isomorphic to projective space. So for that, you need to actually get into construction, which I'll say a little bit more about soon. Yeah, that's right. So in this case, it is reduced, and so the scheme structure is exactly projective space itself. Yeah. So I am being a little bit imprecise by putting all these equalities, but that's on purpose. Yeah. Good question. Thanks for the question.
Yeah. Thank you. And one more thing. So in the definition that closed subscheme Z is inside Pn. So this Pn is n is same as the n in the we have begin with.
Yeah. This n will just be an ambient, like just an n that varies, just an ambient dimension. So there's nothing specific. It's just Pn. So n can be any.
Okay, because we have already begin with Hilbert P, P and K. Okay. Okay. This is NEN.
Yeah, this is just NEN. That's right. Yeah. So as long as you have some Hilbert polynomial, and it does parametrize something in that projective n space, you can define this object.
Okay.
That's yeah.
Okay. Thank you. Thank you very much.
Yeah. No. So this actually brings up a very good question. So that's right. So I've just been talking about sets, and there's not really the valid point is, okay, so if this is just a set, there's no real meaning to this construction, because you could always come up with some variety whose point set is in bijection to some family you're interested in, and you can just call that the moduli space. So what is really going on here? So it turns out that the real power of Grothendieck's construction comes from the fact that this Hilbert scheme satisfies a certain universal property, right? So to explain that, I need to define the Hilbert functor. Okay. So definition. So let P be numerical polynomial, Hilbert polynomial. The Hilbert functor what it does, right? So it's a functor from, let's see, it goes from the opposite category of schemes over K. So you can just think of K algebras for the time being, but I'll write in this generality. And it for each scheme T, it outputs a certain set. And what set is it? So for given any scheme T, it outputs the collection of all closed subschemes over that base T. I'll talk about this in a minute, such that Z is flat over that base. And each of the fibers has Hilbert polynomial P. All T and T. So what is this doing? So I think well, let's just talk about, let's do two examples. So if T was just spec K, this functor is precisely just the closed subschemes in Pn, such that Z has Hilbert polynomial. So it has Hilbert polynomial P. Right. So if you just look at what it does at the point K, it gives you the collection of subschemes of Hilbert polynomial P. But if you look at if you apply this to the arbitrary scheme T, so I don't know, for example, if you think about T being the affine line, this is now giving you sort of families of subschemes or ideals over this base, where each of the fibers has the Hilbert polynomial you're interested in. So let me say that. And we won't need too much of this, but this needs to be here so that so let's see, such that each Z, I don't want to do this. I'll just leave it at that. But are there any questions about this definition though? So that is a functor, and sort of Grothendieck's theorem is sort of really what. So this is exactly what he proved, and it in particular implies what I said on the previous page. It's that this functor is represented or representable by a projective scheme Hilb. So this is what I defined on the previous page. So there is some scheme that represents this functor. Okay? And just so we all know what I'm talking about, by representable, I mean that the Hilbert scheme, the Hilbert functor applied something is just the following Hom functor. Okay, so that set so for each scheme T, I give this collection of flat families. That's equivalent to just the collection of morphisms from T into this classifying space. Okay, So having this functor as a certain Hom set gives you all sorts of universal properties. In particular, I guess there is in some natural sense that its points are in bijection with the collection you're interested in. So this is precisely what's happening. And this construction gives you some scheme structure on the Hilbert scheme. So I'm not going to get into what the scheme structure is, but it turns out in the case of plane curves or hypersurfaces in projective space, that scheme structure is reduced. Okay? So this is kind of where the scheme structure comes in when you prove representability. I might say a few words about this at the end if you have time in relation to our main result. Okay? So why do you want this? So when you want to study the family of some objects, you want to be able to base change or sort of deal with families over arbitrary bases. So you want to sometimes work over the affine line, you might want to work over the affine plane, and so on. And having this fluidity from going from
it may be also good for people who do not know these things to say that there is also a universal object, just to for the representability of the functor.
Yeah. So I'll want to get to that later on when I do it for
okay.
When I do right. So that's so if I don't say later, just remind me. So I'll talk about universal families later on, but just to if it is here. So what was it? So why would we want to do this? We want to do this because when you have a functor sitting around, you can sort of like I was saying, change between bases. And so let's see kind of why having representability makes this useful. So here's an example. So let's look at the tangent space to some point I inside the Hilbert scheme. So if you want to talk about a point of the Hilbert scheme, I'll put square brackets. Okay, and I'll do a lot of examples. So this, even though this sounds like me talking about abstract stuff, it'll become concrete very quickly. So what is a tangent space to a point? So it's the collection of morphisms from the dual numbers to the Hilbert scheme that sends epsilon to I. But thanks to representability, which is over here, this is exactly just sort of flat deformations of the ideal over the dual numbers. So you might be, for example, interested in studying deformations of the dual numbers, and for some reason it turns out that the actual Hilbert scheme is easier to work with, so you would instead go compute the tangent space. Conversely, you might be interested in some scheme. It turns out to be the Hilbert scheme of something. And then to compute the tangent space, you can now instead work with deformations of I over the dual numbers. So this constant change in perspective is why I guess moduli spaces are useful. So if you want to study one, you can somehow, if you want to study the algebra of one thing, you can turn it into some geometric question of the other, of another analogous object. Okay, so that's the kind of goal this is the kind of object you're looking for if you want to sort of study families of some of ideals. So let's actually do some examples. So maybe the first example will be, I'll call it the twisted cubics. So let's see what these Hilbert schemes look like. So I'm going to fix a Hilbert polynomial. So we saw this for plane curves. And I'm going to work in 3 space. Okay. So I'll give you some examples of subschemes of P3 with this Hilbert polynomial. So maybe the most famous example is the twisted cubic itself, which is the, so that's right, which is the 2 by 2 minors of this 2 by 3 matrix. Okay. It's this arithmetically Macaulay variety, and here's a picture of it. Okay. So that's something with Hilbert polynomial 3m plus 1. you can also have another ACM subscheme, and so it's, say, let me put it at the let's say it's a 2 by 2 minus of the following matrix, and this is sort of some non-reduced subscheme, and so this is some non-reduced structure. So yeah, it's literally it's a square of x0 x1, and so geometrically you want to think of this. You want to think of, first of all, its radical, which is the line, and then some non-reduced structure on it. That's sort of the pictorial representation of this subscheme. So I guess here is the affine line, some projective line, and this red stuff is saying that, well, there's some non-reduced structure on this line. Okay, there are more kinds of subschemes here. Let's see. So one thing you can do is you can actually take a plane cubic and an isolated point. So I'm gonna write the ideal like this, and I'll leave it to you to choose a cubic. So choose any cubic in the remaining 3 variables, and then choose some point not on the plane. So geometrically, what this is like sort of a disjoint union of two schemes. So on the one hand, you have sort of a plane cubic, and the other thing you have this P here. So V of I is E, the disjoint union of a plane cubic and a point. So this is my plane cubic. And what is the plane here? Well, the plane is given by this x3. So the plane is V of x3, and this point, just so, I mean, this is the point here. So it is nothing but 0, 0, 0, 1. Is that right? Okay. So this is another subscheme with this Hilbert polynomial, and somehow it's similar to the second one. We can have some funny, at least geometrically funny structure, but maybe algebraically it's not so bad. So it's the following. I'll give the following primary decomposition of this. So it has an embedded component now. We sort of didn't see this in the previous examples. And so what is this geometrically? So again, if you take the radical of this, you get this P1. So it's here. Once again, as an example 2, we have ourselves a non-reduced structure. And this time there's an embedded point. So I will denote it like that. Okay? Sort of saying like, okay, so not only is there this embedded structure along the whole line, but there's also some embedded point structure along that line. Okay? So these are 4, I would say, different kinds of examples of subschemes with this Hilbert polynomial, and you can keep playing this game. So a natural question would be asked, okay, so what exactly, is the Hilbert scheme, right? So the Hilbert scheme is some scheme whose points are in natural correspondence with this and maybe more pictures like this. So the answer to that is given as follows. I want to put this right on the same page. So let me zoom in. So it turns out, as a projective variety, this Hilbert scheme, right? So it's the union of 2 irreducible components. So each thing is projective, but with the plane curves, it happened to just be projective space. It turns out that's not true anymore. So this equality is scheme theoretic, but let me just give you a picture of what the point set looks like. So I'll tell you what the components are in a minute, but sort of you have 2 components, H1 and H2, and I'll tell you kind of where these points lie on. So away over in H2, but not on H1, you have 4. So each of these examples I've given you defines some point inside the Hilbert scheme. So the ideal 4 lies on it by itself in a component, H2. Ideals 1 and 2 lie in a known component. And ideal 4 is something that lies on the intersection of the two components. So I'm not telling you how, whoops, this is 3. So I'm not telling you what's happening. I'm just telling you that, look, there's a theorem that tells you that the Hilbert scheme splits into two components. And these two components meet in some way. And all I'm saying is that taking that for granted, this is where all these examples I've given you lie along. Okay. So what are these two components? So it turns out that at least generically, you already know what these components are. So H1, so the general point of H1 parametrizes. So alternatively, like on an open dense subset of H1, it's actually just a twisted cubics. So the general point of H1 parametrizes twisted cubics. So a dense subset of H1 is in fact just the projective transformations of the standard twisted cubic. So that's actually, and if you take the closure though, remember the Hilbert scheme is projective. So there are some limiting objects of these twisted cubics. For example, thing in point 2. So there is a flat limit that sends the twisted cubic into this non-reduced line. So you have to account for all of that. And H2 is sort of the closure of locus 3. So the general point of H2 parametrizes plane cubics union isolated. Right. Again, this just means that on an open dense subset, an open dense subset is in bijection with plane cubic union isolated points. Of course, you're taking closures, so in the limit, you might get all sorts of funny objects. But this is the theorem. So, and when you show this result, you essentially classify all subschemes with this Hilbert polynomial. So they're more or less just essentially the examples I've given is the set of all things, but I don't want to get into the details of this proof. But does this example make sense? So this is kind of what the Hilbert scheme looks like. Any questions? Oops, I lost it. Okay, let's keep going. So I want to give you,
sorry to interrupt. So this is a subscheme of which projective space in this case?
So that is so there is a that's a good question. So because this is projective, this is going to be the subscheme of some projective space. It's a large projective space. So I don't know what exactly, I don't remember exactly what is in this case, but it'll be something like at least P10, P13, something big. That comes from the construction of the Hilbert scheme. So what you do when you construct the Hilbert scheme is that you embed the Hilbert scheme essentially in some sort of in a Grassmannian, or at least a product of Grassmannians, which will, and then you embed that further into projective space because Grassmannians are projective. Yeah. So the actual project, the projective space itself is not so important. It's just it exists, and this comes from sort of the regularity of
okay.
Yeah, it's related to the Castello-Mumford regularity, and I don't know, other than sort of just cropping up from the construction of the Hilbert scheme, I don't really know of what do I say this way, like the best way to put it. I've not seen like a good answer to sort of like what is sort of, say, for example, the smallest embedding of the smallest projective space into which this embeds. So I don't know the answer to that. It embeds in some projective space, and this comes from the Castle-Mumford regularity. So that's kind of what it is. Yeah. The Hilbert schemes themselves are not. They're not projective space itself. So unlike the plane curve case, these H1, H2 are not projective spaces. Yeah. So any other questions?
Thanks.
Okay. So let's keep going. So you might be saying, okay, so you got two components. What happens? It turns out that like this, these Hilbert schemes get complicated very quickly. So I don't want to spend too long on the next example, but I'll just say a few words. So if you just creep, so you went from, Hilbert polynomial 3n plus 1, so it's like degree 3 genus 0 curves. If you sort of increase the degree by 1, you get a more complicated picture. So rational quartic. So I'll just say just a couple of words on this, not too much. So I've just changed the 3 to a 4, and I'll still assume P3. So what is an example of a subscheme with this Hilbert polynomial? So, maybe the most famous example is the sort of rational quartic, so which is it's a non-Cohen-Macaulay arithmetically Cohen-Macaulay curve. It's kind of embedded in a bad way in space, and usually, I guess you think of this as following. The coordinate ring is the following semigroup, so it's missing s squared t squared. Okay, so this is maybe the most famous example of such a scheme with this Hilbert polynomial. But it turns out that there are like many more such things. And instead of going through a list, I'll just tell you the following. I'll tell you that this Hilbert scheme this time splits into 4 components. Okay, and the component H1, the general member. So as in the previous case, right, on an open dense subset, the general member of H1 is precisely these rational quartics I've described above. As a rational quartic. Okay. But then you have all these extra components. So what can I'll just describe one of them. So H2, for example, its general member is a plane cubic union a disjoint line. So what this means is that on a dense open subset, it's in bijection with the set of all plane cubics union lines. So the point I want to get across is that if you fix the Hilbert polynomial, this Hilbert scheme you get already exhibits interesting in some way, or maybe wild in another perspective phenomenon, right? So going back to the original question, which was like, okay, we wanted to study families of subschemes with some prescribed numerical data. We saw that if we fix the Hilbert polynomial, which we did in these two examples, we get some description of the Hilbert scheme, but we get various types of subschemes, right? You might be just interested in, for example, just the twisted cubics. So you might be only interested in studying families of ideals of twisted cubics, and maybe it's degenerations. So ideals of type 1 and ideals of type 2. Right? You're not really interested in like this disjoint disjoint union of subschemes. So you might be only interested in ACM subschemes in P3, in which case, right, item 1 and item 2 are the only things you're interested in. And you want to consider the families of these objects. But if you go to the Hilbert scheme, you won't just get 1 and 2. You'll also pick up item 3 and item 4. And there's just no way around it, because the Hilbert scheme is sort of this moduli space, and it's a functor, and so it just pops out H1 in H2. So how do you isolate H1 from H2? And and similarly, like, you might be only interested in rational cortex, and you have no interest in these components, right? You want to give some numerical data that will, avoid all the other components. And the way you do that is by basically going to chromology. And I'll briefly say a few words about chromology. So, put a line here, chromology. Oops. Okay, so F is M tilde, a coherent sheaf on projective n space, and M is a finitely generated so all coherent sheafs on projective n space is basically again by the tilde of some finitely generated R module. And so I'm just going to tell you sort of the relation between local cohomology and sheaf cohomology. I will stick to sheaf cohomology because I guess it's a little bit easier to write down our main results, but it can all be done in terms of local cohomology. So I'll just kind of, just so that we have it here once, here's the relation between the two. So the zeroth and first local cohomology is related to first H0 in the following exact sequence. And the higher ones are isomorphic up to a twist. Okay. So I will say everything in terms of sheaf cohomology, but you can do this translation and for all I, at least one. So you can do this translation and you can state similar things in terms of local cohomology. All right. So why do I introduce cohomology? Right. So it turns out that cohomology does indeed sort of separate, in this example, items 1 and 2 from items 3 and 4. So we'll see this in two ways, but maybe it's a simple geometric way to see this is as follows. So I'll say example twisted cubic, continued, right? So so this was the twisted cubic, right? Let's say it's a twisted cubic. So this is some connected subscheme. So it's so the zeroth, so just the global sections is just one dimensional. It's just a fact, connected and projective. And if on the other hand you were that plane cubic union an isolated point, then there are two connected components, and it turns out that there are sort of two global sections. I mean, dimension of the space of global sections is two-dimensional. Okay, so sort of quite simply, already if you just take into account just the global sections, you already see the difference between the twisted cubic, which is, I guess, item 1, and item 3. Okay, so it's kind of that was very naive, but it turns out that like by actually asking for precise cohomological data, you can actually refine the Hilbert scheme. So I'll just sort of say this as a goal. So construct a universal scheme, well, construct a scheme that parametrizes subschemes of Pn with fixed Hilbert polynomial, but we want more now. So we Hilbert polynomial and fixed chromological data. Okay. So that's what we're looking for. So we want to be able to sort of isolate these components in these examples that we've seen. Okay, and we want to do this again in some in a universal way. So we wanted to represent a certain functor, and I'm going to describe all of that. So just as we did with the Hilbert scheme, I'm going to define a certain functor. So since we're going to be sort of encoding all the cohomology, as you'll see, I'm just going to actually just fix the following notation for the rest of the talk. So let this just be a tuple of functions. So each hi is just a function with
Ritvik, I have a question.
Yeah.
Yeah. So here you are fixing the dimensions of all the sheaf cohomology modules starting from S0.
Yes.
So that in a way determines the Hilbert polynomial also, right?
Yes, that's right. Yeah, it does.
Okay.
So yeah, that's right. So the Hilbert polynomial is sort of this alternating sum of these objects. That's right. So
right.
Yeah, I wrote this in I wrote it twice on purpose, but yeah, that's a good point.
Okay.
If you fix cohomological data, you've already fixed the Hilbert polynomial. I agree.
Okay.
But I just want to drive home the point that I am sort of going to sort of start by fixing the Hilbert polynomial and then sort of refine it further.
Okay.
Yeah, thank you. Be a tuple of functions. Okay. And so I'm going to define the following functor. Where it go? There it is. So I'm going to define, it's called fib, so it's going to be fiberfull. This is a fiberfull functor. And once again, I'm going to sort of go from schemes to sets. And what it does is, so previously we saw this as taking closed subschemes that are just flat. But now I'm going to actually ask for more. And again, I don't want to get into the details of what all these objects are, but the correct notion so when you want to, so why did we have flatness before? Okay, let's step back a bit. When we were looking at families of things of the fixed Hilbert polynomial, because we're talking about families, we wanted to make the notion of families precise, we enforce some sort of flatness condition. Similarly, if you want to talk about families of things with a fixed cohomology, we need an analogous flatness condition on all the cohomologies. Okay, so the right notion here is to ask for all the push forwards to be flat, and I'll just say locally free since everything is equivalent, and maybe this is how it's presented in the paper. So all the high push forwards are locally free over T. So what is FT, right? That's a good question. Yeah, and if you don't know what, and if you haven't seen this, just don't worry about what this is, but just think of this as the correct family notion. So FT here is what do I want? Oh yeah, it's the base change of X with T. Okay, so we want that, and then of course we want the dimensions of the cohomology groups to be the same. So the first condition tells us that we are sort of families, and the second condition is the dimensions of the cohomology groups are what we want them to be along all the fibers. Okay? This is a little loaded, but we sort of need this at least at the level of functors, and then we can talk about what happens at the level of points.
But what is X here, Ritvik?
Oh, shoot. Sorry. Yeah, you're right. X is not X. It's just Pn. Thank you. Yeah, thanks. But there is no X. It's just Pn. Yeah. So I was sort of getting ahead of myself, but the point is that this construction of Grothendieck can be applied to any projective variety. And I'll say a few words in a few minutes, but that's what that X was. But for now, everything is just Pn. And so, yeah, this is defined in such a way that at least at the level of points, you better be what I want you to be. So at the level of points, this is exactly what we want. So this is the closed subschemes of projective space over K, such that the dimensions of the cohomology groups for all possible twistings is exactly HI of V. Okay, so this is what we want at the level of points, but of course, to have a more robust definition, we needed to base change correctly, and that's the definition above. Okay, so this is the refinement of the Hilbert scheme, and one of the main theorems of our paper is in fact that this functor is representable, similar to Grothendieck's Hilbert scheme. So theorem, let me write it like this. Right, so it was mentioned that if I fix the cohomological data, the Hilbert polynomial is determined. Indeed, so that's given because by the alternating sum of the HIs. So assume that this alternating sum is a numerical polynomial. I mean, this is just there to make sure that you don't just throw random functions, right? You want these functions to actually, at the end of the day, actually be the cohomology of some subscheme, or else you just get yourself an empty Hilbert scheme, and that's pointless. So you assume this is a numerical Hilbert polynomial, and then we have the following. So there is a quasi-projective. So now it's not projective anymore. It's just I mean, it's only quasi-projective. There's a quasi-projective scheme called fib H Pn, called the fiberfull scheme. So this is the object of the talk. That represents the functor which I've defined above. Okay, and so not only is it quasi-projective, but it's quasi-projective in a certain way as a subscheme of the Hilbert scheme. So inside here, so this sits inside here sort of by construction, more or less. And it's actually locally closed inside here. So that's the result. So I want to say a few words about this. So it's actually quite non-trivial because what we're doing is we're enforced. So we start with the Hilbert scheme, which just fixed the Hilbert polynomial, and then we're sort of enforcing all the cohomological dimensions to be exactly what we wanted. And that's not finitely many conditions by any means, right? And trying to control all the cohomological data is way more nuanced than just controlling the Hilbert polynomial. And it's sort of also related to lots of recent work in commutative algebra. So this looks kind of, looks like a gentle generalization of the Hilbert scheme. And it is a natural generalization of it, but to actually get into and proving this, you actually need to do some. You need to do a lot of technical technical computations to actually get this to work. And this is because you kind of want to control cohomology over arbitrary bases. And it's not so clear how you do this when, for example, the base is non-reduced. Okay, so there is a lot that goes into this. And we don't have too much time, so I'm not going to sort of even touch the proof unless there are questions later. But I want to just say a couple of more words about this theorem and then talk about some examples and applications. So as stated, this is sort of just about the Hilbert scheme. And I want to say that this is not sort of the generality it's stated in the paper. So what you can do a couple of things. The first thing is you can, well, you can replace the Hilbert scheme, right? I was talking about projective space. You can first of all replace this with the Hilbert scheme of any projective variety. So if you're a projective variety X, you can always talk about subschemes of X with that Hilbert polynomial. So you can do this relatively. And this can be sort of generalized further to quote schemes, which I really don't want to get into, but well, so shoot. You can do this X. Talk about Hilbert schemes over K, but you can also talk about Hilbert schemes over an arbitrary base, arbitrary locally Noetherian scheme. And you can sort of generalize this even further to quote schemes, which sort of parametrizes quotients of coherent sheaf supported along a certain locus. And you can kind of do the fiberfull scheme in all these instances. So this is the fiberfull scheme we saw here. You can kind of upgrade it and get a fiberfull scheme over here. And that's why I had S floating around, X floating around, sorry. And there is an analogous fiberfull scheme in all these situations. Okay. So in all of these situations, it's locally closed. And so yeah, so basically the generality in which the quote scheme was defined by Grothendieck is the generality in which case is the extent, is the generality you get for the fiberfull scheme, right? So any sort of questions about the statement of the theorem? So let's move on. So I have about 7-8 minutes. Yeah, let me talk about something else next. Okay, so now that we have this, and yeah, now that we have this, let's see. Yeah, let's see what we can do with this. So the one thing you can do with this is actually use this to parametrize at least algebraically interesting loci. So one interesting loci, at least that I find interesting, is the locus of, say, arithmetically Cohen-Macaulay varieties. So so let's see this. So let's see how I want to do this. I want to do this in the shortest possible time. Yeah. So okay. So if I have a subscheme of Pn and it's arithmetically Cohen-Macaulay, right? That just means that the coordinate ring is Cohen-Macaulay. And so it's known that for arithmetically Cohen-Macaulay things, because it's Cohen-Macaulay, that the only relevant cohomological information is in the 0th dimension and in dimension D. So let D be the dimension of Z, then all the middle cohomology vanishes, and the only interesting cohomology is in dimension 0 and in dimension D, and all the intermediate cohomology vanishes. Okay, so with this fiberfull scheme, we can actually now try to find just the parameter space for all ACM things with prescribed cohomological dimensions, and we could state it sort of as a corollary of the previous thing, but I'm going to sort of state it slightly differently. So we're given two functions, H0 HD, we can define the ACM functor. And so what is this? So I'm just going to choose things inside the fiberfull functor. Whoops. So remember, the fiberfull functor requires all the chromological data. So I know that until d dimensions, all the middle chromology vanishes, and again, it vanishes after. So that's all the chromological data of an ACM thing, and I want such thing to be ACM for all t. Okay, and then sort of a theorem or corollary, however we want to see it, is that this functor ACM is represented by an open subscheme of the fiberfull scheme. Which I also call ACM of the fiberfull scheme. Okay. Once again, well, yeah, I'll just not say anything about that. So that's what's true. And you can also do this, for example, with arithmetically Gorenstein subvarieties too. And so what this allows us to finally do is that now if you wanted to study ACM, ACM subschemes, you can finally, well, depending on what you want to study, at least for algebraic, certain algebraic questions, you can now work with this parameter space rather than the whole Hilbert scheme. So in the case of twisted cubics, right, that's something that was ACM. What happens? I won't say too much because we don't have too much time. I'll just say that that Hilbert scheme we saw before splits off into two different fiberfull schemes. So we indeed got a refinement, and I'll just say what these things are. So this one over here. So you might not remember what H1 and H2 were, but if you do, I'll tell you what this fiberfull scheme is. But this is all the ACM subschemes. And so open. And this is, I guess, was the component H2. So its general member was plane cubic, isolated point, and it's closed. Okay. So it does kind of separate the components of the Hilbert scheme, and there are many more examples, but which you can find in the paper. In the last 2 minutes, I just want to talk about maybe something which we're planning on studying in the future, and maybe if you're also interested, and you can look at is fixing one of the, I won't say problems, but sort of compactifying the fiberfull scheme. So for most purposes, right, well, for algebraic purposes, it is now nice to sort of work with these fiberfull schemes if you want to, say, study twisted cubics or rational quartics instead of the full Hilbert scheme. But for maybe some geometric purposes, the Hilbert scheme is still, that component of the Hilbert scheme is a better option because it's projective, right? So if you want to just sort of study all degenerations of these twisted cubics, you might still need the component of the Hilbert scheme. This component here only has the ACM degenerations, and it is indeed open, right? And you might sometimes want an actual compact space. So the next step, which is something we're planning on actually doing at some point, is to actually compactify this. So if we kind of actually compactify, then we have truly, I would say, replaced the Hilbert scheme completely. I mean, maybe that's too strong, but I'll leave that as a question. So problem, compactify. So I'll just say compactify the functor. Compactify the fiberfull scheme So fix the only issue it has compared to the Hilbert scheme. So i.e. define some functor n and show it is representable by a projective scheme. Pn over k, right? And maybe the ideal result would be to actually get that component of the Hilbert scheme back. So maybe, so if you're sort of familiar with Hilbert schemes, then what I'm asking is the following. So I'm kind of asking that maybe, is it possible to compactify it inside the fiberfull scheme? So the thing is, the new thing, and the thing I want here is I want it to represent a functor, right? All these, you can always take the component of the Hilbert scheme to be the compactification of the fiberfull scheme. That's always there for you, right? Because it is a sub-scheme of the Hilbert scheme. But that's not as useful as having it actually representable. So we want that closure to be representable by, to represent some functor. Okay. So I think I am basically out of time. But in summary, what I want to say is, you have the Hilbert scheme, which is good for studying things with fixed Hilbert polynomial. But if you want to have more refined data, for example, you want to study just ACM subschemes, you might want to consider this fiberfull functor, depending on what questions you want to study. And there are lots of open questions for this parameter space, because it was only recently constructed, right? Like, as I mentioned before, trying to control all the chromological data is complicated, which is kind of why it hadn't, I guess, been done before. And so now that we have this, you can kind of ask all the similar questions you ask for the Hilbert scheme for the space. For example, study deformation theory of this functor. So, before people have studied a lot of deforming ideals I. Now you want to deform an ideal I along with all its cohomology groups. And you can study some of its geometric properties inside the fiberfull scheme. Okay. All right. I will stop here.
So let's give a big hand for Ritvik. And are there any questions, comments?
Yeah, I have two questions.
Mm-hmm.
So for each Hilbert polynomial, we have a unique Lex segment ideal, which has the same Hilbert polynomial, and that is also obtained by some sort of deformation. So in which component does that lie?
Yeah. So so it lies. Okay. So let's see. Yeah, the Hilbert. So you have the usual Hilbert scheme. So right. So as long as it's in projective space, there is this Lex segment, like this lexicographic ideal, which is sort of this unique Lex segment ideal with that Hilbert polynomial. And in this case, it's unique because I'm assuming it's saturated. And so yeah, the Hilbert scheme is splits into like a bunch of components, but there is a distinguished component that contains the Lex ideal. So there is a theorem, let's say by Rees and Stillman, and which says that the this lexicographic ideal is a smooth point inside the Hilbert scheme. Is a smooth point of the Hilbert scheme. So what this means is that it actually lies on a distinguished component, right? So there's no, so you can actually talk about the component that consists of this lexicographic ideal. So you might have this Hilbert scheme that's very complicated, right? I don't know, maybe it looks like some horrible, bizarre thing, right? And let's, just to make it worth, add some non-reduced structure here and there. But this theorem tells you that all the way somewhere in some component, there's this Lex ideal, and it's nice and smooth. So that is there. And of course, that has some specific cohomology, and the fiberfull scheme might or might not contain this point. So if so in the case of the twisted cubic, right, there's only one Lex ideal for that Hilbert polynomial. So this one contains the Lex ideal, but this one does not. So that's kind of the picture here. So for the Hilbert scheme, it is there, and it's somehow distinguished. Does that answer your question?
Yeah, thanks. Is a precise answer. Yeah, I have one more question. One can ask for a multigraded version of the same result.
Yeah. So I mean, I haven't thought about it. So I think it's possible, but you have to be a little careful here, because the so it's possible, but not exactly as written. So the way sheaf cohomology and things work, it's sort of best suited for saturated things. That's why we're working inside the Hilbert scheme. But I think it is possible to ask the analogous question for multigraded things too. So it should be possible. We haven't done it, but
yeah, I mean, even in the multigraded thing, the sheaf cohomology data determines the multigraded Hilbert polynomial.
That's right. Yeah. So it should be doable, but I haven't we haven't bothered to do it yet. Yeah.
Okay. Thank you. Thank you very much.
As far as I am aware, I haven't. I'll have to think about it, but I've not seen a reason to not.
I mean, Jairo is expert on multigraded things.
Oh no! I'm sorry, Ritvik, but I think it won't be possible.
Won't be possible
because no. I mean, so there is a classical example of cohomology of Katzmann, where you have cohomology in a bigraded setting, and then there is infinitely many associated primes. And so there is some trick. I mean, in our case, in our projective setting, when you take the relevant ideal, it's like the whole positively graded part, no?
That's right.
And in this case, there won't be. But I mean, in cohomology, for instance, in biprojective setting, the ideal with respect that you compute cohomology is the intersection of one of here and one of here, no? So
yeah, I guess, yeah.
So no, I don't think. But I mean, with this example of Katzmann, that there is infinitely many associated primes, that could be a problem.
Okay, thanks. Thank you.
There you go. So we hadn't thought about that. That's I guess that gives you some problems you might come across. So it's a subtle issue.
Any other
Ritvik,
questions?
I have one question. So in the result of your here on, you are fixing a sequence of
Yes.
numbers, and then you are looking at all possible subschemes which have this cohomological data.
Yeah, that's right. Yeah.
So instead of that, if you just fix one say numerical data and just look at all subscheme which have let us say ith cohomology as this number. So if you parametrize that thing, so how it will behave?
Yeah, it's the so that's the same thing. So that's also fine. So again, that'll be if I'm not mistaken, should also be represented by something quasi-projective. So that's not going to cause an issue. So this is the most refined. This is the most refined thing. So this is the hardest one to deal with. So
Okay.
yeah, those are all easier to deal with.
Okay. And one more thing. So this you have said something about the Gorenstein subschemes. So I'm asking in the Hill case. So how does this like you have talked about ACM? So if you look at arithmetically Gorenstein things, so how it sits inside Hill?
Yeah, so it's so sorry. It's also open. So the point is that you can so all your let's see. So first of all, for being so since you're so the ACM things are already open, right? So inside the ACM locus, you're sort of asking
you have
for
Gorenstein,
you're asking for Gorenstein things. That's right. So you're just asking for the last chromological dimension to be 1. And so that's some sort of upper semi-continuity thing. So it's somehow open inside that. And that's all there is to it there. Yeah.
Okay. So it is still open, right?
Yeah, it's still open. That's right. Yeah.
Okay. And what can you say about denseness of
so it won't be dense. So then I mean, okay, so the I need to be careful when I say this. Denseness. So wait, by denseness, do you mean the denseness of this ACM thing inside the fiberfull scheme?
Or no, I was not in the fiberfull scheme. I was in the Hilbert scheme.
Yeah, so in the Hilbert scheme, the answer is no. So already with this twisted cubics, right? That's kind of one of the motivations for this discussion. The ACM stuff is over here. It's not H1. It's inside one component. So the ACM stuff is just over here. Its closure is not the full Hilbert scheme. You have sort of this whole component of non-ACM subschemes, which is kind of why you wanted to construct the fiberfull scheme in some sense. People don't just it's very uncommon that people are sort of studying this component. It's both algebraists and geometers are sort of would be interested in this component most of the time. And so you want to kind of isolate the ACM stuff. Yeah. So it's not dense.
What about in that fiber scheme? That
yeah. So so in the thing is, the fiberfull scheme itself is not projective. So that you can still talk about denseness, but is it dense in there? Let me not lie to you. I believe it is. If I'm not mistaken, I believe it is dense inside the fiberfull scheme. Yeah, if I'm not confusing myself, I should not be confusing myself, but I believe it is inside. It is indeed dense inside the fiberfull scheme. Yeah. But it's not empty though. I mean, it's like yeah.
And what can you say about the singular locus of this?
Yeah. So the singular. Okay, so that's a good. So yeah, I have a dumb answer and I have a better answer. So the dumb answer is that its singularities in general are just as bad as the Hilbert scheme, and that's because the fiberfull scheme. So let's look at points. So let's look at the Hilbert scheme of points in projective space. So I don't know. The Hilbert polynomial is just say some C for some constant, and let's say in Pn. Of course, if you just have points in projective space, there's no hierarchical homology. So we can just talk about the fiberfull scheme of also I'll just say C, because there's only zeroth cohomology and it's all just constant C. So we can talk about the fiberfull scheme, and it turns out that the Hilbert scheme of points is basically the fiberfull scheme. Sort of scheme theoretically, there is no, it's not just a set, and it is known. Well, by recent work, it's known that for n large enough, right, this kind of satisfies Murphy's law. So it's very singular. This is very singular, so it has arbitrarily bad singularities. So as a consequence, so does the fiberfull scheme. Now, but that doesn't mean this is true in general. And so this is something we have, which is, I guess, future work, but it is possible that sort of in special cases that it might be. So I don't know. We don't know if in special cases it's necessarily less singular than the Hilbert scheme, but it'll need to be investigated. But in full generality, it's just as bad as the Hilbert scheme, because the Hilbert scheme of points and the fiberfull scheme of the points are the same. So whatever singularity you get for the Hilbert scheme of points, you also get it for the fiberfull scheme. It doesn't. This was made to fix the Hilbert scheme has two problems. The first problem is that it's too many components, and the second problem is that it's singular. In my perspective, the first problem is worse than the second one, because the first problem just comes from the functor. The second one also comes from the functor, but you can in many cases desingularize stuff, and that's okay. But the first one is the annoying one, because you end up with lots of components, and half the time you don't even know if you have you don't even know if you don't know if you have enumerated all the components. So the fiberfull scheme sort of deals with the first problem, that by restricting cohomology, in many instances you're sort of just left with one component that you care about. Right? So that's kind of what it does, but it doesn't really fix the singularities issues, at least so we have not really investigated to what extent the singularities of the fiberfull scheme is related to the singularities of the Hilbert scheme. But here's an example where it's basically identical. Does that sort of give you some idea of?
Yeah. Thank you very much.
Anything else? Okay, let me ask one thing. And what is fiberfull scheme, and is more or less similar to fixing the resolution of the sheaf, or OZ?
It's okay. It's a little bit. So it's like a, how do I say this? It's I mean, it's a little bit more than that. I mean, it's I guess less. It's more than that, right? Because what happens is that you can have the same resolution, but your cohomologies can jump, right? So your free resolution, the Betty numbers might be the same,
so that is slightly different, but I mean, more or less they have to be similar, but you can put them together and can get a new functor, right? That means, I mean, you can have fiberfull scheme plus fix the resolution, right?
That's right. So yeah. So we've not.
You get a finer functor.
Yeah, so we like vaguely thought about this, but sort of we were busy doing this. We didn't sort of iron out any of the details of that. But that is a valid point. So there's indeed another functor. So whether that's representable in the same way, we'll have to think about it. But it is there. You're right. It's you have to do some work. It's not exactly the same, because they're related, but the subtle differences is kind of where, like, as I guess Yaron mentioned, with sort of going to the bi-grading, you have to be careful to kind of actually see what works and what doesn't work. But it's to be determined.
So if there are no other questions, shall we thank the speaker once again?
Thank you very much.
Thank you.
Thank you.
All right.
Okay, thanks, Mohan, for sharing.
Thank you.
And thanks to Ritvik for making this talk so concrete and understandable. It is not easy to make these things so concrete. Yeah.
Thank you.
Very
Yeah,
nice.
it was
Thank
fun. Yeah, thank you.
you. Okay.
Thank you.
Bye-bye. Bye-bye.
Bye.
Bye.
Bye.